Okay, let's have a look at part 2, which is going to look at sort of the complexes of coordination compounds. So we look at in part 2, we're going to look at the complexes, we're going to look at ligands, denticity, and coordination number. So it's generally going to be an overview of these things, not really considering how they react, but just generally like talking about like how a complex is formed, what is a complex, what are some common ligands, what are common some denticities, what is denticity, and then looking at how these correspond to coordination number. So the rows of the second elements of the second row in the main group, lithium to neon, follow the octet rule by forming chemical bonds that normally attain a share of 8 electrons. So mimicking the closed shell configuration of a noble gas. In this case, for the second row, it's neon. So generally, like they want to share electrons in some way that they can form a full orbital. For first row of the D block, the next noble gas is krypton. So that would be argon plus these electrons. That's 18 electrons. So many stable transition metal complexes have a total of 18 electrons. So the metal D electrons plus electron pairs from ligands, and this is the so-called 18 electron rule. It's a good indicator of transition metal complex stability, but it's not the only indicator. Like there are stable compounds which have 17 electrons or 16 electrons. Generally, though, we don't go above 18 electrons. That's sort of like the only real hard and fast rule. Although, of course, as everything, there are exceptions, but generally that involves delocalized electrons and systems which are more complicated than what we'll typically encounter here. So most of these bonds, most of the ligands that bond to a metal center are doing so as Lewis bases. They're typically donating electrons to the metal, which is acting as a Lewis acid, which is an electron pair acceptor. We typically draw these bonds with an arrow pointing from the ligand to the metal to indicate that even though it's a covalent bond, we're not getting one electron from the metal and one electron from the ligand. In fact, what we're getting is both electrons in the covalent bond from the ligand. So complexes. The chemistry of D block transition metals is dominated by the ability to form complexes. These were first considered by Alfred Werner in the 1890s. So metal complexes consist of a central metal surrounded by a set of ions or molecules, such as called ligands, bound to the metal. A ligand provides a lone pair of electrons to a vacant d orbital on the metal. So this is where it's acting as a Lewis base. And so this donation of electrons to form a covalent bond is called a dative or coordinate bond. We've seen that before in Lewis acid base theory, where we saw how ammonia formed a dative covalent bond to boron trifluoride. And this type of chemistry is called coordination chemistry due to the reliance of the coordinate bonding between metal and ligand, and it can be related to acid-base chemistry. So ligands are electron pair donors, they're Lewis bases. Metals are electron pair acceptors, they're Lewis acids. So here is an example complex. So cobalt is acting as a Lewis acid, where it is accepting 6 lone pairs from 6 ligands. These 6 ligands are ammonias. Ammonias are, we know, Lewis bases. They have a lone pairs of electrons which can be donated to the metal, like so. So here we have the lone pairs of the ammonias all indicated, and then we can see here that they form dative covalent bonds. So the 6 ammonias are in the inner sphere complex. The whole unit is described as a complex. There must be anions such as 3 chlorides to counterbalance the 3+ charge in the complex. And these are not formally attached to the metal center and considered to be outer sphere complex ions. So this is cobalt 3+, is indicated by the 3+ outside of the brackets. The brackets indicate that this is one total ion. So this must be considered as one whole species. We cannot just consider the cobalt, we must also consider the ammonias. And so this is an inner sphere complex. But because of this 3+, everything exists as a neutral species. So there must be counter ions. So those counter ions could be chlorides, they could also be bromides, they could be basically anything that sufficiently balances the charge. In this case, we're assuming that they're chlorides. There must be 3 of them, 3 -1 chlorides allows the balancing of that charge. Other examples, depending on the charge of the metal and the ligands, the complex can be neutral, cationic, or anionic. So a neutral complex such as chromium fluoride, this nickel dichloride dicationic, such as this complex which we just had, or this hexa-aqua nickel 2 complex ions, such as hexacyanoferrous 3, or this one which is tetrachlorocobaltate 2. So complexes that have only one type of ligand are called homoleptic. So, like for example, in our cobalt complex from the previous slide, we had only ammonia ligands, so that would be a homoleptic compound. Ruthenium here has 3 bipyridal ligands, and so this is also homoleptic. Complexes that have 2 or more types of ligands are called heteroleptic. So this one where we have ammonia and chloride, 2 different types of ligand. In this instance, the chloride is acting as a ligand and not just as an outer sphere ion. And then here we have various different types of pyridine ligands on the ruthenium, and that's also heteroleptic. But what are ligands? So usually the metal is trying to find those 18 electrons, so it only has so many from its elemental d electron count plus the whatever electrons have been removed, get those other electrons from some other place. And so they're generally found from ligands. Ligands are generally Lewis bases capable of donating electrons to the metal center. Generally, they're shared because are not super electropositive, so they're capable of having electron density. Some ligands, some of neutral ligands, such as ammonia, water, pyridine, which is 12. Or there are also common anionics, so fluoride, chloride, cyano, hydroxide, and thiocyanate. Some ligands are capable of bridging. So when bound to a metal, they still have electron pairs available for donation to a second metal atom, and they're capable to bridge between 2 metal atoms, so they can be called bridging ligands. So here we have 2 platinum metals and then 2 chlorides which bridge across them. This nomenclature down at the bottom with the mu indicates that we have a bridging chloride or a bridging chloroligand. Here we have mu imide, so that's indicating that this is bridging as well. Then we have mu oxygen, so oxygen is acting as a ligand here. Here we have mu pyrazine. This is acting obviously as a bridging ligand between these 2 iron complexes. Don't worry so much about this. This will be explained more whenever we get into naming of complexes further on. So the ligands here on this slide are all what are called monodentate ligands. They all form a maximum of 1 dative covalent bond or coordinate bond with each metal center. This one here is bridging. It's technically forming 2, but it's not with the same metal. It's with different metals. So it's only what's called monodentate, which means 1 byte. Dentate comes from the Greek meaning like byte. And so monodentate means 1 byte, so it takes 1 byte out of the metal. So the chelate, or chelating ligands, chelate from the Greek meaning claw, is a ligand containing 2 or more donor atoms that can simultaneously bond to a transition metal ion. So generally, these are more stable. We'll talk about their stability in a later session, but generally these are more stable than monodentate ligands. That's because you have to break 2 bonds to the metal center as opposed to just 1. And there's the possibility after you've broken the first bond in the chelating ligand that it just reattaches again before you break the second bond or the third bond. There's also a stability gain from forming 5 or 6 member rings. So 5 and 6 membered rings are most stable as smaller or larger rings are too strained. So the 5 or 6 member ring, the angles are not too bad. So a ligand with one donor atom is said to be monodentate. So that's your kind of chloro or your kind of ammonia ligands. 2 donor atoms are said to be bidentate, 3 donor atoms tridentate, 4 tetradentate, 5 pentadentate, and 6 hexadentate. So common ligands then, so monodentate ligands then, so a lot of nitrogens, a lot of phosphorus, they're all in the same group, group 5. So ethylamine, common ligand, pyridine, again, another common ligand, triphenylphosphine, a very common ligand, triethyl phosphite, also a pretty common ligand. 1,2-diam, okay, then bidentate ligand, so 1,2-diaminoethane, so it's commonly abbreviated as ene. So you need to be aware of these abbreviations because really they are much more used than not. It's rare that you actually get the full name written out. So to an extent, especially these first 3, you really do need to know what they correspond to. So, and that they correspond to a bidentate ligand. So ene is 1,2-diaminoethane, 2,2' bipyridine is bipi. 1,10 phenanthroline is fen. We also have glycinado, which comes from the amino acid that's commonly abbreviated as gly. Oxalato, which comes from oxalate, which is ox. And then acetyl-acetonato, ACAC, is also a very common ligand. Again, probably need to be aware that that is a bidentate ligand. Tridentate, hexadentate, don't get a lot of heptadentate, but or tetradentate, but they do exist. Tridentate, diethylene triamine, diene, 2 'prime, 2 double prime terpyridine is terpy. Hexadentate, this one, a very common ligand, EDTA, used in a lot of applications. It's actually used in a lot of medical applications as well. As a way of just removing ions that you don't want to be there. It's very good at coordinating metal ions in solution. So for example, the reason for this is because it forms a hexadentate complex. So if you think most of these coordination compounds form octahedral complexes, which is 6 bonds. This is one ligand which can form 6 bonds. And so once it forms, it's very difficult to remove because in order to remove the EDTA, you need to break each one of those 6 bonds. So you need to remove 6 coordinated bonds without having another one reform. So it's called ethylene diamine tetraacetato. Acetato. Really, it's just that's the most common name. That's the most common way of referring to this. But yeah, you need to be basically the ligands that I'm telling you about. You need to be pretty aware of. Tetradentate, quite a few. I guess you've probably seen a trend here. Most of the ligands that we talk about are nitrogen ligands or oxygen bonding ligands. So trine is tris-2-aminoethylamine or amine. So trine, so it has 4 nitrogens, 1, 2, 3, 4, each with a lone pair, each capable of bonding to a metal. 1,2-bis salicyladine aminoethane, saline, again, nitrogen with a lone pair, nitrogen with a lone pair, and these 2 oxides. They're capable of forming 4 bonds to a metal. Silcam, here, again, same thing, 4 nitrogens, all with lone pairs. And then porphyrin rings, so this is porphyrin, the simplest, this commonly referred to as porph. So this is an analog of the way that iron is held in hemoglobin. So typically an iron metal would sit in the middle here. And then that's kind of how hemoglobin, the complex, is structured. So metal oxidation states, so the formal charge remaining on a metal when all the ligands are given their usual charges. So for example, here in permanganate, so this is going to be -2 for the oxides times 4 is -8. So this is -1 overall. So this must be +7. So oxygen is typically oxide, so it's O2 minus, fluorine, fluoride, F minus. Ammonia is neutral. Cyano is cyanide, negatively charged, and then carbonyls are neutral. So what will be the oxidation states on the metal? So here, -2 times 4 is -8 here. -1 times 6 is -6 here. 0 times 6 is 0, and so on. So this would be +7. This would be +6. This would be +3 because of the 3 plus oxidation state here. This would be +2 because this is -6 in total. Here, this would be 0 because this is 0 and it's overall neutral. And here we have, I think this is a typo. Okay, no, it's not. So manganese -3, so it would be the -3 oxidation state. But the formal oxidation state does not indicate the true charge on the metal. It's just a formalism. So it's not really a manganese 7+ ion here. Not really. It's just a formalism for us to or to account for the electrons, I suppose. So the coordination number is defined as the number of donor atoms associated with the central metal or atom or ion. So here we have a platinum complex with 1, 2, 3, 4 ligands. That's a coordination number 4. Chromium here has 6 ligands, 3 hydroxides, 3 water. So it's coordination number of 6. Here we have a coordination number of 6 as well. This is ethylene 1, 2 diethylamine. It's a bidentate ligand, so it takes 2 bytes per ligand. So there's 3 times 2 is 6. So even though there's only 3 En, it's actually a coordination number of 6. And here the silver has the 2 ammonias, so there's a coordination number of 2. So numbers from 2 to 9 are known for D block transition metals, but most typically it's usually just 4 to 6. So here are some of the common geometries. So these are similar to the ones that we'll have seen in earlier VSEPR studies. So the geometry here for a coordination number of 2 is linear. Coordination number of 3 is trigonal planar. Coordination number 4 is tetrahedral. And square planar. 5 is trigonal bipyramidal. Examples of those: octahedral geometry. You also have another one which is trigonal prismatic, although this is really rare and requires a very specific shape of a ligand. So one that's like this. So this, like for example, the sulfurs would be here, and then it would go like this. So it would go like something like that, and then something like that, and then in the back here, something like that. That's really the only way to form these kinds of complexes, and it's still not even that common, because this is only capable because normally you could do like something like this in an octahedral complex, but because of the specific shapes of the metals and like the rhenium and the ligand here, we kind of don't see it form an octahedral complex, but only really see it form trigonal prismatic, which is very rare. Pentagonal bipyramidal for 7. So we already saw that right at the start, which was our heptacyanovanadate. Then we have a capped trigonal prismatic like this, so dodecahedral, Archimedean antiprismatic, hexagonal bipyramidal, tricapped trigonal prismatic for 9. These are really uncommon, and you can see that most of the time when they're formed with very small ligands. So like here, it's formed with fluorides, which are small, cyanides, which are small, and then hydrides, which are also small. And so that was part 2, which is where we'll end it for this part. So part 2 topics were complexes, ligands, denticity, and coordination number. So the next time we'll be talking about more on coordination complexes in part 3.